Hello everyone, today I want to show an example on finding a moment on a 3D block. So as you can see, we have our X, our Y, and our Z axis where our block is sitting on. And from there we have 5 forces acting on that block. We have our dimensions. It has a height of 0.5 meters. Then we have that 1 meter width, 2 meters of length. And so when you're trying to find a moment on a 3D block, what you want to do is you want to calculate the resultant moment of that 3D block about each of those axes. So what you're going to be doing is you're going to be doing the same step 3 times. You're going to find the moment of a block about the x-axis, the y-axis, and then the z-axis. Or you could start off with the z, y, x, it doesn't matter. But you want to do that for each and every axis. So I usually like starting with the x-axis, then going with the y, and then the z-axis. So that's what I'm going to do first. I'm going to be finding that resultant moment about that x-axis. So basically what that means is since I'm working with that x-axis, what I'm going to be drawing, the sketch that I'm going to be drawing for that resultant moment about that x-axis is going to be this right here. Since I'm viewing it from that x-axis, that's what I'm going to be seeing of that 3D block. Since I'm finding the resultant moment of the x-axis, I'm going to be taking the resultant moment about this point right here, since that's what's laying on the x-axis. So I'm going to be doing it about that point. From there, I'm going to be drawing our forces where they would be according to this view of the x-axis. The only force that is not going to be shown is that 400 newtons since it is parallel with that axis. And from there, the dimensions that we're going to be using is the 2 meters and the 1 meter, because from there you don't see this side of the box, so you don't need that dimension. So our first step is finding the resultant moment about the x-axis. As you can see, I drew out what I showed you guys, this box, taking the resultant moment about that corner that lies on that x-axis and the 1, 2, 3, 4 forces. So here we have our corner right there. 1, 2, 3, 4 forces. We know that this side is 2 meters long. This side is 0.5 meters of height. So now that we have that sketch drawn out, we can proceed to finding the resultant moment. Remember, counterclockwise is positive. So our resultant moment about the x-axis is equal to, we have this vertical 50 Newton force that is not going to be creating a moment since it is already parallel or lies on that vertical force. So that distance is going to be 0, meaning it's not going to be creating a moment because a moment is equal to the force times the distance. So that's just 0. We're not going to write it out. From there, we have this 200 newtons that intersects with that um, y-axis of that point. Once again, our distance there is going to be 0 meters. So once again, that's not going to be creating a moment. So the only two forces in this scenario that's going to be creating a moment is the 300 and the 100 newtons. They're both going to have a distance of 2 meters. The only thing that's going to be different is whether it's going to be positive or a negative moment. For the 300 newtons, we have an upward force, meaning that that's going to be creating that counterclockwise moment, meaning it's going to be positive. And then for the downward force, that's going to be creating a clockwise moment, meaning that one's going to be a negative moment. So we have a positive moment of the 300 newtons, that's our force, times our distance of 2 meters. And then we have a negative moment of that 100 newtons times the 2 meters of distance once again. And once we solve for that, we end up getting that our resultant moment about our x-axis is equal to 400 Newton meters going counterclockwise. So just like that, we were able to determine our resultant force about the x-axis. Now we're going to be doing the same thing for our y and z axis. So now we're going to be finding the resultant moment about the y-axis. Our y-axis is right here. As you could see, the point that is sitting on that y-axis is this point where that 100 newtons is going downwards. So we're going to be taking moment about this point right here, that corner. And since we're doing the resultant moment about the y-axis, this is what we're going to be drawing, this side of the block. From there, we're going to be drawing out the 100 newtons coming down from this corner, that 300 newtons going up, the 50 newtons going down, and the 400 newtons. From there, that 200 newtons is not going to be shown in that sketch since it is parallel to the y-axis. And for our dimensions, we're going to have that 0.5 meters of height and that 1 meter of length. So we come down here to our sketch. We could move this upwards. Okay, as you can see, we have this side of the box. I could have drew it a bit longer, but you get the point. This is the 0.5 meter height or 1 meter of length. We have that 100 newtons coming down for that point right there that lies on the y-axis. We have this 300 newtons going upwards from that corner. We also have the 400 newtons going to the left from that corner right here. Now, I decided to draw this 50 newtons um, down at this corner. You could have also just drew it up here coming like this. I just didn't want it to be stacked so we could just see it a bit better, but it does not matter where you draw it for a vertical force in this scenario because remember that moment is equal to the force times that distance. So if I drew it up here or if I keep it down here, either way, that distance is going to be this 1 meter. Does that make sense? That it's that 1 meter, so it's not going to change anything. When it comes to a horizontal force, you could draw that. You could draw that 400 newtons, for example, in this case. Also on this side, right here, remember, always going the same direction. So since that 50 newtons was coming downwards, I drew it downwards. That 400 newtons, since it's going to the left, it shall be shown going to the left because either way, that distance is always going to be that 0.5 meters, and you want it going in that same direction because a 400 Newton force right here is going to be the same because it's going to be creating that counterclockwise moment, while this moment over here also going to be creating that counterclockwise moment. The force is the same and the distance is the same. So that's why I'm just explaining why I decided to draw my 50 newtons down here instead of up here. You guys could also draw it up here. It is up to your choice. You just want to make sure that that moment is not going to be changed. So now that we drew out our sketch for our y-axis, from there, we know that this 100 newtons is not going to be creating a moment since the distance is equal to 0. So there's no moment with that force. But from there, all these other three forces are going to be creating a moment. So we know that counterclockwise is positive, and our resultant moment about the y-axis is equal to, we're going to start off with this 50 newtons. 50 newtons. The force is 50 newtons. The distance is 1 meter. From there, it's going to be creating that counterclockwise moment. So it's going to be a positive moment. So we have a positive moment of 50 newtons times the distance of 1 meter. From there, we have that 300 newtons going upwards. Once again, the distance is going to be that 1 meter. From there, that's going to be creating a clockwise moment since it's going upwards. So that means that's going to be a negative moment. So we have a negative moment of 300 newtons times 1 meter. And lastly, we have our 400 newtons. Our 400 newtons has a distance of 0.5 meters. From there, it's going to be creating that counterclockwise moment, meaning it's going to be positive. So we have a positive moment of the force of 400 newtons times the distance of zero point 0.5 meters. From there, we add up all of our moments, so we end up getting that our resultant moment about the y-axis is equal to negative 50 Newton meters going counterclockwise, but we want to deal with positive numbers, so our resultant moment about that y-axis is 50 Newton meters going counterclockwise. And just like that, we were able to determine our resultant moment about that y-axis and its direction. So we have now found that resultant moment about the x and the y-axis. So now we just have to do that once more for our z-axis to be completely done with this example. So here we already have our sketch of our z-axis, as you can see. But let's go back to our sketch. So remember, now we're going to be taking that moment about the z-axis. So our z-axis is right here. So we're basically going to be looking like from above that block. So what we're going to be seeing is this top part of that block. Our this corner right here lies on that z-axis. So that's where we're going to be taking that moment. From there, we're not going to be showing that 50 newtons, that 300 newtons, and that 100 newtons since they are parallel to that z-axis, so they're not going to be shown. The only forces that are going to be shown is this 400 newtons on that top left corner going to the left, and this 200 newtons going upwards on that corner. From there, the dimensions that we're going to be needing is that 1 meter and that 2 meter for 2 meters this length, 1 meter that length. So we're going to go back down to our sketch. And like I mentioned earlier, here is the corner where we're going to be taking that moment. Since it lies on that z-axis, we have that 400 newtons going to the left from that corner, the 200 newtons acting upwards on that corner. We have our 1 meter and our 2 meter of dimensions, and now we can proceed to finding that resultant moment. So remember, counterclockwise, positive, and our resultant moment about that z-axis is equal to, for this 400 newtons is not going to be creating a moment because it intersects to this axis right here. So remember, our distance is going to be 0 for this horizontal force. So that means that that moment is going to be 0. So we don't have to write that out. From there, we only have then the 200 newtons creating a moment about the z-axis. So our force is of 200 newtons. From there, our distance is this 1 meter right here. So it could be aligned parallel to that axis. From there, it's going to be creating a clockwise moment. I'm sorry, a clockwise moment. So that means it's going to be a negative moment. So we have a negative moment of simply 200 newtons times the 1 meter. Those are the only forces creating a moment about that z-axis. So we end up getting that our resultant moment about the z-axis is equal to negative 200 Newton meters going counterclockwise, but we want that in positive numbers, meaning that we have positive 200 Newton meters acting counterclockwise about that z-axis. And now we're completely done with this example. We have found the resultant moment of that 3D block. And we were able to find that resultant moment about the 3D block because remember, we found the resultant moment about those three axes, the x, y, and the z axis and its direction. So remember, you could have started off with whichever axis. You could have started off with first our z, then our y, then our x-axis. It doesn't matter. Just remember to find that resultant moment about those three axes and to find its direction as well. Thank you guys so much for watching this video. If you guys liked watching this video, please hit that thumbs up button. And if you guys would like to see more of this type of content or videos like these, please feel free to subscribe to our channel. Thank you guys so much.